Now let's take the discussion forward and let's see that again U is a function of temperature and volume. So now let's differentiate it again. So you'll have du is equal to curly U upon curly T at constant volume, okay, into dV. Now this is not dV, this is dt, sorry, not dV but dt. Let me write it down again. So this is dt because we are differentiating with respect to t, plus curly U upon curly V at constant temperature into dV. Alright, now we know that this term is equal to 0 because the internal energy will not change as the volume changes if the temperature remains constant. So this is a given value to be 0. So this means that du is equal to curly U upon curly T, okay, at constant volume into dt. So this is an expression that you get. And if you look at this particular term only, then you can say that curly U upon curly T, that is the rate of change of internal energy with respect to temperature at constant volume, is equal to the specific heat capacity at constant volume. So this is a definition that is there for CV. So when you substitute this value over here, so we would get the value of du as CV into dt. Now this equation, it holds good for an ideal gas for any process, whereas for any other substance which is not an ideal gas, this equation is true only for a constant volume process. Okay, so this is something you should always know about. Now since CV, that is this value, it is constant only for an ideal gas. Alright, so I can also write it down as delta U is equal to CV into delta T in terms of differential notation. Now let's talk about the enthalpy. Now we know that enthalpy is equal to U plus PV. Now I can also write down enthalpy as U plus RT because PV is equal to RT. Okay, this means that H is only a function of temperature. Okay, only for an ideal gas. Okay, so this means enthalpy is a function of only temperature only for an ideal gas. Now if you take this equation forward for further analysis and differentiate it, you get dH is equal to du plus R into dt. Now wondering why we did not differentiate R, because R is a constant, remember that. Okay, now what is the value of du? The value of du is CV into dt. So let's put this value over here. So upon substituting the value for du, I'll get dH is equal to CV into dt plus R into dt, which will give me CV plus R into dt. Alright, so this is again an equation worth looking at and remembering. Right, now since H is a function of only T, okay, and we can define that the specific heat at constant pressure, this is equal to curly H upon curly T at constant pressure. So this is the value of, or the definition of Cp. So I can say that dH is equal to Cp into dt. Okay, so this means that if you compare this equation with this equation, you can say that Cv plus R is equal to Cp. Alright, so you can say Cv plus R is equal to Cp, and you can then further write it as Cv minus, or you can say Cp minus Cv, not Cv. So you'll have Cp minus CV is equal to R. So this is a very, very important relationship that you should always remember. Now this equation, that is dH is equal to Cp dt, it holds good for an ideal gas even when the pressure changes. But for any other substance, this is true only for a constant pressure change. Okay. Now this is the difference of the specific heat capacities. Now let's talk about the ratio. So if you have the ratio, which is Cp upon Cv, so this ratio is of importance in ideal gas computation and is designated by a symbol gamma. So this is again a very, very important term to understand and remember. Or you can also rewrite it as that Cp is equal to gamma into Cv. Alright, so from this equation, if you take this equation, I can substitute the value of Cp in here and I will get gamma into Cv minus Cv is equal to R. Okay, and this becomes gamma minus 1 into Cv is equal to R. So the value of Cv then becomes R upon gamma minus 1. So this is a very important value or a result that can be remembered as it is. Alright, so this is again a very important mathematical relation. Now we know the value of Cp is equal to gamma into Cv. So let's rewrite it. So Cp is equal to gamma into Cv, and I already know the value of Cv, so let's substitute it over here. So I will get gamma into R upon gamma minus 1. So if you have to rewrite these values in a nutshell, so you'll have Cv is equal to R upon gamma minus 1 and Cp will be equal to gamma into R upon gamma minus 1, and the units of these are kilojoule per kg Kelvin. Now these values, which are this is value of R, so this is the characteristic gas constant. Okay, now we know that the characteristic gas constant is equal to the universal gas constant upon capital M. Okay, so similarly I can have few more values, or you can say few more mathematical relations for it. So I can write down Cv bar, which is equal to M into Cv. Okay, so this would now become capital M into R upon gamma minus 1. Now M into R, if you look at this equation, is R bar, that is the universal gas constant. So this is what you get. Okay, similarly if you want to find out Cp bar, this is equal to capital M into Cp, which is equal to M into gamma into R upon gamma minus 1. So still you can combine M and R, and this would give you gamma into R bar upon gamma minus 1, and the units for these you can say specific heat capacities or molar specific heats. Okay, this is kilojoule per kg mole Kelvin. So these are molar specific heats. Okay, so this is the video on the topic of internal energy, specific heats, and the enthalpy of an ideal gas. Now in the next video, let's talk about the entropy change of an ideal gas.